This case is about radiation pressure. Chinese is called 网压. Actually, when surface intercept electromagnetic radiation, force and pressure are exerted on the surface. So sometimes when you are under a spotlight, you feel that there is some pressure from the light, and actually you can really feel that. And if the radiation is totally absorbed by the surface, the force is something like this. And if the radiation is totally reflected, the force is double, which means that originally it has some radiation pressure. If this is the object and there is a EM wave going here, and then you totally absorb. So this is IA over C. If you really need to absorb, if you really need to diffract it, which means that it go back with another IA over C, which means that totally you absorb. So you have 2 IA over C. Because IA over C going this way, if it is totally absorbed, it is this term. If you really need to diffract it, so then you absorb 2 IA over C, and then IA over C really going back. This is a delta. So which means that which is why when it is totally refracted, the force is double. The force is double. And the radiation pressure is the force per unit area. So then we try to divide the intensity by the speed of light. So if you really want to derive it out, it is something like F. The force is the dp dt. This is the power. The power. You take the derivative. This is then it is something like 2 delta U over C over delta T. And delta U is something like 2 IA delta T over C delta T. So it will finally become 2 IA over C. this should be the momentum rather than the momentum, because this is the Newton's law of motion. This is the Newton's law of motion, which is this is F equals ma. So ma can be written as dp dt. So the next topic is about the polarization. Polarization is something like if the EM wave are polarized, if E field vector are all in single plane, called the plane of oscillation, the light wave from the common source are not polarized. That is, they are unpolarized or polarized randomly. Which means that, okay, for this one, this is unpolarized, so that there are many different E field in different direction. Something oscillating like this, something oscillating like that, and then you try to sum all of them together. Then you will see, this is the horizontal direction of the E field. This is the vertical direction of the E field, and this one is the polarized EM wave, which means that you can only observe the E field in only one direction. For example, in this case, it is polarized in Y direction. And as you know, the E field and B field are always perpendicular to each other in the EM wave. So if E field is unpolarized, B field is also unpolarized. If E field is polarized, B field is also polarized. So if E field is something like that, the B field is something maybe like that in zero direction. But here, these two are both E field. These two are both E field. And this is something tricky part. I think I showed you a video a few weeks ago about the polarization. And here, this is the polarizing sheet, which means that only one direction of the E field can go through this, or I can say it a filter. So that originally the incident wave is an unpolarized light. You have both directions, and this filter is direct vertically, so that after passing through this filter, the light is polarized vertically. And here we have an equation like I0 is the incident, is the intensity of the incident wave, and I is the intensity of the wave that goes through the filter. If the original light is initially unpolarized, then the transmit intensity is half of the original. So we have one half. And if the original light is initially polarized, the transmitted intensity depends on the angle theta, which means that in this case, E is polarized in this direction, which has an inclined angle with the y direction, theta. So so after going through the filter, the intensity will become I0 cosine theta square. Cosine theta square. And so far it is reasonable and matches to our intuition for the classical physics. But later on, there is something very strange happen, which is related to the quantum mechanics effect. So here is another sample example. So first, if we just ignore this one, that's only I0 and I2. No, I0 means the incident wave here. If you just ignore the second one, this two is perpendicular, so that there should be no light can go through this one. However, in this case, we have another filter which has a 60 degree with this one. Then finally, you'll find that there are some EM wave can go through the third filter. So this figure shows a system of free polarization sheet. In the path of initially unpolarized light, the polarizing direction of first sheet is parallel to the y-axis, and the second one 60 degree counterclockwise, and the third one is parallel to the x-axis. What fraction of the initial intensity of the light emerges to the first sheet system, and in which direction is emerging light polarized? So before sheet 1, so it is unpolarized, and with the intensity I0. And after sheet 1, so it is polarized, but in y direction, and the intensity become half. So after the second one, after sheet 2, so it is polarized with 60 degree from y-axis, and actually I2 is I1 cosine square 60 degree. So cosine 60 degree is 1/2. So 1/2 square is 1/4. And I1 is actually 1/2 of I0. So it finally becomes 1/8 I0. And finally, after the third one, it will become polarized in x-axis, of course, and I3 will become I2 times cosine 30 degrees squared. And 30 degree, cosine 30 degree is square root of 3/2. So square is 3/4. And so finally the answer will be 0.094 I0. So there's actually some EM wave can go through the third one, which does not match the intuition sense if you consider it in classical physics, because you feel that there is some EVU going this way and EVU going that way, and we brought this one, which is the vertical polarized, and we brought this one, which is horizontal polarized. Then it shouldn't be any wave going through this three, but actually you insert this one in between them, and some of the waves can go through. And it is actually based on the probability. So next one is what you should have learned in high school. I think this is the so first it is the refraction, 反射. So so if you have a two material, for this case, this is air, this is water. So a photograph showing an incident beam of light refract by a horizontal wave water surface. So you know that the incident angle and the refracted angle should be the same. It is easy. And yeah, you see this. So I suppose you should have learned that. And also you can see this beam. So that this is called the Snell's law. So that you see n1 sine theta 1 equals n2 sine theta 2. And n1 and n2 is the dimensionless constant called the index of refraction, which is inverse proportional to the speed of light in that material. So in the air, n would be close to 1. I think I put it here. So for air, 1.00029, vacuum exactly 1, water 1.3, and diamond 2.42. So that's why for ladies like diamond very much, because you can try to track some of the light inside, and then it will look beautiful. Well, yeah. So I suppose you should have learned that before. So well, here this is called the chromatic dispersion. Actually, for different wavelength of light or different frequency of light, the angle or the speed would be, or the speed of light would be a little bit different. So that as you can see here, this is a white light incident to here. You see that the refract angle for the red light is larger, and for the blue light is smaller. So that you'll be able to see the rainbow, or if you use a stream, you will be able to see something like the rainbow-like spectrum. So it is not difficult to understand. Blue is always bend more than red. So that's why we use the red light to specify caution for the traffic light or something, because the red light will not bend as much as the blue light. So in other sense, red light is better to go through something like the steam or something like that, or and here we talk about the total internal refraction, 全反射. As you know, for this equation, if for example, if n2 is larger, then theta 2 should be smaller. I mean, if n2 is larger than n1, theta 2 should be smaller. So, for example, if you have an incident wave from the water to the air, then the refracted angle should be larger than the incident angle. So if you try to make the incident angle very large, then the refracted angle will be 90 degrees or even larger. The point at for the refracted angle larger than 90 degrees, then it is called the total internal refraction. And actually, it is not. The wave is actually refracted to the original material and do not really follow the Snell's law. Actually, you can use the Maxwell equation to derive all this stuff. If you use the Maxwell equation with a boundary condition, you can really solve what is the polarization of the incident wave perpendicular and parallel to this surface, something like that. You can really write it out. So this is called the total internal refraction. As the incident wave has a large enough angle, then the reflection wave have a angle larger than 90 degrees, then it will refract it backward. And there is another phenomenon called the frustrated total internal refraction. Here we know that if it is larger than 90 degrees, it always going backward. But actually, it's not really the same. Total internal refraction is something like this. If you have another same of the primes, which is far enough, then the wave cannot really go through this one, and all the wave total internal refraction. And if this one is close enough so that these two surfaces touch each other, then the wave should go through. However, if these two surfaces is very close but not really touching each other, then part of the wave will refract and part of the wave will go through. And actually, if you really use the Maxwell equation to derive, the EM wave in this gap is actually decaying exponentially. As long as this gap is narrow enough, some of the waves can go through this gap, and will just go outside, and part of it is reflects. So this is called the frustrated total internal reflection, and you can check it something here. But actually, this is not really important for you. So this is the table. I just let you have a look. And typical crime gas. Okay. So there is an other phenomenon called the Brewster angle. Brewster angle. Brewster angle is something like theta b equals arctangent n2 over n1. And if this which means that will be fully polarized. Well, if the incident angle is theta b equals to this one, which means that the incident angle and the refracted angle add up to be 90 degree. Add up to be 90 degree. And in this case, the reflected wave will be polarized, will be linear polarized. So a ray of unpolarized light in the air is incident on a glass surface at Brewster angle. The electric field along that way have been resolved into component perpendicular to the page and component parallel to the page. So the yellow dot means it is perpendicular to the page, and the arrow means it is parallel to the page. So the reflected ray only consists of the component perpendicular to the page. But for the refracted wave, it is partially polarized, which means that some of the component perpendicular to the page still can go through this surface, but for the reflected wave, you can only observe the component perpendicular to the page. Let's try boundary. So here we have another additional example. So an unpolarized light is sent to a system of three polarizing sheets. The angle theta 1, theta 2, theta 3 of the polarized direction are measured counterclockwise from the positive direction of y-axis. Angle 1, angle 3 are fixed, but angle 2 can be varied. So this one and this one are fixed, but this one can be rotated. The intensity of the light emergence from sheet 3 as a function of theta 2. Scale in the intensity axis is not indicated. What percentage of the light in initial intensity is transmitted by the system when theta 2 is 30 degrees? So first of all, we need to know what is theta 1 and theta 3. And theta 2 is varying, but if theta 2 is 0 degree, this is 0. For other, you cannot really make sure how large it is, but for 0 degree, 90 degree, and 180 degree, you make sure that the output intensity is 0, which means that when it is 0 degree, either the first one or the third one is perpendicular to it. And when it is 90 degree, either theta 1 or theta 3, either the first one and the third one is also perpendicular to it. Which means that the only possible solution is theta 1 and theta 3 is proportional. Is perpendicular. Is perpendicular. One is at 0 degree. One is at 90 degree. For example, but it doesn't really matter which one is 0, which one is 90 degree. So we can just assume theta 1. We can just assume theta 1 is 0 degree, theta 3 is 90 degree. It doesn't really matter if you just swap it, the answer will be the same. But if theta 1 is 0 degree and here theta 2 equals 0 degree, so the wave after passing through theta 2 and go to the will all be blocked by shift 3. And when theta 2 is 90 degree, all the wave go through theta 1 will be blocked by theta 2 because either of them are perpendicular. So when theta 2 is 0 degree, so this is 0, this is 90, then all of them will be blocked. And when this is 90 degree and this is 0 degree, all the wave will be blocked also. So this matches these 2 points with this assumption. So it tried to ask you when theta 2 is 30 degree, how much light can really go through the third one. So actually, IF, the final intensity divided by the original intensity. So because originally it is unpolarized, so after passing through the first one, it is 1/2. And passing through the second one, it is 30 degree. So we multiply it by cosine 30 degrees squared. And after passing through the third one, this is 30, this is 90. So we multiply by cosine 60 degrees squared. And the answer is actually the same as the last sample problem, 0.094, or we can write it as 9.4%. Any questions? Okay, so we have next one. A certain helium-neon laser, 氦氖镭射, emits red light in a narrow band of wavelength 632.8 nanometer with a wavelength width of 0.1 nanometer. What is the corresponding frequency width for the emission? It tells you that, okay, the light is a sine wave, of course, and the center of the wavelength is 632.8 nanometer. And actually, it is not a delta function. It really has some width. Ouch. Something like this, because the well is not perfect. So this width is something like 0.01 nanometer. This is the lambda. And you know f and lambda are inverse proportional to each other. C equals f lambda. So we can write f equals c over lambda. And so we can write df equals dc over lambda. And c is a constant, so we can write it like minus c over lambda square d lambda. So we just take the derivative. And we can write delta f is c over lambda square delta lambda. So c is 3 times 10 to 8 over lambda. Lambda is 632.8 times 10 to minus 9 squared times wavelength width is 0.01 times 10 to minus 9. So the frequency width is 7.69 gigahertz.